So now let's say, let's introduce the simplest magnetic field case, this one. Okay, so now the, oops, keeps doing that. Okay, so now this one is the magnetic field. The charge is moving to the right. And then the magnetic field is also to the right. 1 Tesla. So what should the force of the charge be? F equals Q V crossed into V. So this is the simplest magnetic field case. So if the velocity is to the right and the magnetic field is to the right, V and V, what's the force of the magnetic field? Remember we said that the cross product of those two is just equal to 0. So the force is 0. That means it should just keep going to the right at constant speed. So this is kind of like when I did my user-defined case, when it just kept going at a constant speed. You see? So this is the weird thing about magnetism, is that the magnetic field doesn't even feel the presence of that charge. Look at what's going to happen. The charge just simply goes to the right. At constant speed. And it takes 4 seconds to get to the right. Exactly. See, remember that's what happened when I had the user-defined case where I put the E field was 0. You see that? Okay. Cool, Joy? You're still there?
Yep.
That's cool or no?
Oh yeah, definitely.
Okay, good, good. Okay, how about the next kind of case? Bx is 1, Bz, By is 1. That's another, oh, that's like that. Vx is 1, Vy is 1. So now what do we expect the path to be? Let's do it before we actually run it so we don't cheat. So if the Vx is this way, and which direction is V? Is it in the Y? Yeah, it's in the Y. Right? It's into the board. So then let's do the cross product, Vx, right? Into the board, cross it into the B because B is going into the board, and then the vector is up. So I would expect the force to be up like that. So then what's going to happen? The charge is going to start curving like this. The initial force on it will be to the up like that. Then by the time that the charge gets here, the charge is moving this way. Remember, B is always into the board. Then the cross product to the left. So you see, the force is always staying centripetal to the path. It's always staying perpendicular to the path. So that's why the path of the particle is a circle. It goes like this. Okay, so I would expect the path to be like that. Let's check that out. Press play. We got it. You see here, this is the force vector. Beautiful, beautiful. Okay, it took 6 seconds for it to make 6.28 seconds for it to make one revolution. Does that make sense? So, and then what does the radius look like? Well, remember from the middle of the screen to the top edge was about 2 meters, right? To the top edge. So the radius looks like it's about 1 meter. The radius looks like it's about 1 meter. So let's make sense of that. The radius experimental is 1 meter. And then the time, the period of the oscillation, because this is an oscillatory motion. It's repeating, right? It keeps going. So the period is 6.27 seconds. Okay, so how do we calculate the theoretical radius? Okay. You say the force is equal to QBB sine of theta is equal to mv squared over r. All right. So the force is, remember, the Q, the B, cross product with the B, right? The B is into the board. So QBB sine theta, and the angle between them is 90 because the V is into the board and the V is like this. So their angle is 90. So this is 1. And then the V cancels this V. And then we have an equation for the radius, mv over qb. Okay? And in our case, what do we have? The V is 1. The B is 1. And then the Q over M ratio was what? Yeah, it was 1, right? 1 coulomb per kilogram. Oh, then that's it. Q over M ratio is 1 times 101, 1 meter. So the theoretical radius is 1 meter. Right? So that's what we are getting, right? This is where it would be nice to do some user, because I don't think we can have yeah, see, when you're on this one, you can't change things too much, but you could go like this, user defined. Then you could say, okay, let V be 1, and then let the B be 2. If I make the B twice as large, what should happen to the radius? Double the magnetic field, what ended up happening? When I doubled the B field, the radius was half as much, right? It curved quicker. So that made sense. The circle became like this. You see? So it made sense that if I'm stronger B field, the radius is smaller. You see? Okay, so now that's one level easier, is we're testing out this equation, and we can see that it goes in a circle. Okay, now the next one, maybe we could try, is the, let's do the, what is this one? Bx is 1, By is 1, Bz is 1. Is it still going in a circle? by is 1, bz is 1. Oh no, it's an ellipse. That was, what was it, 6.27 seconds? How do we determine that? How do we determine the theoretical period? The circumference, 2 pi r, over the velocity, right? So if it's going at a velocity of 1 meter per second, and the radius was what? Radius is 1 meter, right? No, radius is, yeah, the radius is 1 meter, and the velocity is 1. Oh yeah, so then the theoretical period would be 2 times 3.14, 6.28. So remember the other one had a period of 6.27. Okay, so that's pretty much it, good. So now in this case, what do we have? We have Vx is 1, Vy is 1, right? And then what Bz is 1 also. Bz is 1 Tesla. So we have like Vx is this way, Bz is this way, okay, and then By is into the board. So due to each magnetic field component, you have a different force, right? So due to the Bz, you have V crossed into Bz out of the board. Oh, it looked like an ellipse because we were looking at it with that angle. Let's see here. It's actually a circle. It's actually a circle in 2 planes. So what's going to happen is that it's making the 2 circles. If you think about it, it's making 2 circles. One, it's going this way. Vx is to the right, right? And it's making the circle out of the board. So it's coming out like this. And its radius is 1 meter like this, okay? And then it's also making a circle like this. So it's kind of a combination of the two. It's like this, and it's almost like in this plane. It's a tilted plane, 45-degree tilted plane like this. So how would you do the general cross product here? Half is equal to Q, V crossed into B. You would say equals MA, right? So then you would say here, Q over M ratio is just 1, so that's gone. And then the components of the V vector is going to be 1, 0, 0. So that's how to do a general cross product. 1, 0, 0. And the components of the V vector is 0, 1, 1. And then that's going to equal to the acceleration. All right, and then that's equal to velocity squared over r. Okay, so then you're going to have here, what's that here? This one you covered it. The determinant of this is just 0. So you do I hat 0, 0, 1, 1 minus j hat 1, 1, 0, 0 plus k hat, and then cover this, 1, 1, 0, 0 is equal to the A vector. Okay, so then you have here, this one disappears, minus J1 plus k1, and that's equal to a. So a back, the acceleration is in the j and the k direction, right? And that's equal to v squared over r. So therefore, the magnitude of the acceleration is going to be what? So the a vector is negative j plus k. The magnitude of the acceleration is going to equal square root of 2, and that's going to equal to velocity squared over r. And therefore, in our case, the velocity is 1, right? 1 squared. And then the radius is going to be 1 squared over square root of 2. Oh, nice problem. 1 divided by root 2. 0.707. And the period of the motion is going to be what? 2 pi r over the velocity. And so 2 pi times 0.707 over 1. Times 2 times pi divided by 1. 4.44. 4.44 seconds. Okay, let's see if we run that, whether we're right. Okay, let's go like that. Which one were we doing? By is 0, bz is 0. Okay, so I'm gonna time to see how long one revolution takes. Ready, go. It should take 4.44 seconds. It's actually a circle, but it looks like an ellipse because it's in the YZ plane. Ready? Yep, 4.44. Ha! And then the radius is 0.707. Yeah, makes sense. It's a little bit more than a half. See, the size of this arrow is done so that it's about half of the distance to there. So if it had been half of the up to this arrow tip, that would have been a radius of half a meter. So now if you want to see it as a circle, you have to kind of tilt it. You see, like this, kind of. See how it's tilted at 45 degrees? And go like that. See, it's a circle. Oh, wonderful. Wonderful 3D simulation. Yeah. Okay, how about one more one for today? Let's make it helix.